Hello all of you. So in the last lecture we started doing the grand canonical ensemble, that is when the chemical potential, volume and temperature are the control variables that refer to an open system, and we derived the expression for the most probable distribution. So we will take that discussion further this day and find how can we find the average properties for the grand canonical ensemble. So essentially what we have discussed so far is the most probable distribution, that is given as the number of systems with energy E and J and number n is given as A multiplied with exponential of minus beta E and J minus gamma n divided by sum over n sum over j exponential of minus beta E and j minus gamma n. Beta is argued to be the same as 1 by kBt, because the constraint for the energy is the same as the canonical ensemble. Gamma we haven't discussed so far, that it is a Lagrange multiplier, but we do not know what exactly it signifies until so far in the discussion. So now, just like what we did in the canonical ensemble case, again we can refer to the denominator as some kind of a partition function that is clearly different from the canonical ensemble case, but we can give it some name still. Let me call it some z, and let me call it the grand canonical partition function. So even though the function is defined a bit differently in the canonical ensemble, the properties of the function remains the same as in the canonical ensemble case, that is z is still a normalizing function and that we can see because the probability of a state or a system having E and J energy and n molecules or n particles is given as A and J factorial by A in the most probable distribution, and that is given as exponential of minus beta E and J minus gamma n by this z. It ensures that the probabilities add to 1, that is if I do summation of n summation over j p and j, then the numerator will have the same summation as denominator, they will cancel and this will be equal to 1. So by using this partition function we can still normalize the probabilities, and it is still also a generating function, and we will see how it works out in this case. So let us say if I start with z as summation over n summation over j e to the power minus beta E and j minus gamma n. In the earlier case we said that dou ln q by dou beta is minus of the average energy, right. In the grand canonical case it will be simply q replaced with z. So dou ln z by dou beta happens to be minus of average energy. Let us see how it is true. So if I take the dou ln z by dou beta, it is 1 by z, derivative of this guy. So you have summation over n summation over j, and then derivative with respect to beta. So, exponential will come as it is, and then derivative of the exponent with respect to beta, that will give me minus E and j from the first term and 0 for the second term, because gamma n does not depend on beta. So, this is pretty much minus of summation over n summation of j E n j multiplied with P n j, because this is how we defined the probabilities. The probability was simply exponential of minus beta E n j minus gamma n by z. It automatically appears right here. So, this is equal to minus of E bar, right. So, although the ensemble has changed, the control variables has changed, but the relation between the average energy and the partition function is the same. The partition function itself is different for the grand canonical ensemble, but the relation relating the average energy with the partition function is the same. We can still use partition function to generate the properties of interest, in this case the average energy. We can also do it for other properties. So, let us say if I do dou ln z by dou v, we expect to get something like pressure, and this is equal to 1 by z summation of n summation of j e to the power minus beta E n j minus gamma n. And now the derivative of exponent with respect to volume, that will give me minus beta dou E n j by dou v. This E is still the internal energy, and we know that d E n j for any system is equal to T d s minus the pressure, let me call it P n j of that, dV plus summation over j mu j d n j. So, if I take dou E j by dou v, that is equal to minus P n j, and therefore, I can write it as beta summation of n summation of j small p, that is the pressure, multiplied with the capital P, that is the probability of the particular state, and this clearly is the average pressure P bar. So, it is the same relation that we have got with Q replaced by Z in this particular case. Now, since there is an gamma appearing here, we can also compute a derivative with respect to gamma that we could not do in the earlier case, because it is a new variable coming in the grand canonical case. So, let us see what that gives us. So, if I start with the same Z, and if I compute dou ln z by dou gamma, that is 1 by z summation of n summation over j exponential of minus beta E n j minus gamma n, and now derivative of this with respect to gamma, the first term will not contribute and second term will give me minus of n, and this is essentially equal to minus of summation of n summation of j n multiplied with the P n j, the probabilities, and that is minus of n bar. So, in this case we can also find the average number of molecule in the systems or average number of particles in the system as the derivative of ln z with respect to gamma. In this case, this n is also a variable. So, you will have fluctuations in n and you will have some average value of n that also can be computed using the partition function. So, essentially until so far I have demonstrated that even for the grand canonical ensemble, Z works like the both the normalizing function and the generating function, and the same idea is true for also other ensembles that we discuss later. So, always keep in mind that if I know Z, then I can find all the properties of interest, but the properties themselves that we can evaluate from there depend on the choice of ensembles. Let us say average number of particles does not have any meaning in the canonical ensemble case, because the number of particles was the control variable. In this case, number of particles can fluctuate or vary between state, and therefore, average number of particle is a meaningful variable in this case, and that we can evaluate using the partition function. Now, if I go a bit further from there, we can also notice that this Z is actually a function of my E and J, beta and gamma, and again it is like for all possible values of E and J, that is like a multiple energy values, and beta and gamma are single values. So, now I can define a quantity ln of Z. Let me call that quantity G. So, I can define the total derivative dG as dou G by dou beta at constant gamma, constant energies, plus dou G by dou gamma at constant beta E and J, and this has to be multiplied with d beta, and this has to multiply with d gamma, plus summation over n, summation over j, because we have multiple energy values for different states, dou G by dou E and J at constant gamma and beta d E and J. And we can evaluate this partial derivatives. Let us see how we can do that. So, G is equal to ln of Z. So, G is essentially ln of summation over n, summation over j, exponential of minus beta E and J minus gamma n. So, we can find dou G by dou beta as 1 by Z, summation over n, summation over j, exponential of minus beta E and J minus gamma n multiplied with minus E and J, and this we already have said is minus E bar. Similarly, we can do dou G by dou gamma, and we already said that this is equal to minus n bar. The last one, dou G by dou E and J, that will be equal to, so now this will apply only to one of the terms right here, and that term is when energy is equal to E and J. For all the other values in summation, this will not contribute to the derivative. So, this will be 1 by Z e to the power minus beta E and J minus gamma n multiplied with minus of beta, and that is minus beta P and J, that is the probability of that particular state. So, therefore, I can write my dG as minus E bar d beta minus n bar d gamma minus beta summation over n, summation of j, P and J d E and J. Now, the last term is something that relates to the work done in this particular case. And why is that? Because every state will gain energy with dEj, and therefore, the net change due to the work is given by P and J dEj, just like what we had for the canonical ensemble, and macroscopic term, this is equal to minus p bar dV, that is the work done, right. The same thing that we have done for the canonical ensemble as well. In this case, the only difference is that we have an extra summation over n, just because we have varying number of molecules, but the argument remains the same as earlier. So, therefore, what we have is dg is minus E bar d beta minus n bar d gamma plus beta p bar dV. Now, let us define a quantity g plus beta E bar plus gamma n bar, and if I take a total derivative of this quantity, that will be dg, that is minus E bar d beta minus n bar d gamma plus beta p bar dV plus the total derivative of these things, which is beta dE bar plus E bar d beta plus gamma dN bar plus n bar d gamma. We have certain cancellations here, and essentially what we get is beta dE bar plus beta p bar dV plus gamma dN bar. Now, we can move the beta to the left hand side, and what we have is 1 by beta d of g plus beta E bar plus gamma n bar is equal to dE bar plus P bar dV plus gamma by beta dN bar. Now, let us compare with the definition of ds that we have used earlier. So, basically we can write dE as TdS minus PdV plus mu dN. Keep in mind that we had a summation earlier, but now we are looking at only one component. So, I only have mu dN. If we are doing a multi-component case, we simply have to also put a summation in this term over the number of species. So, this will give me ds is dE plus PdV minus mu dN. So, if I compare this expression with this expression, by the way there is TdS here, with this expression we can say that my gamma by beta is my minus mu, and therefore, gamma, which was not well defined so far, it was a Lagrange multiplier, but there was no physical significance, actually is related to the chemical potential. It is minus beta multiplied with the chemical potential. And if I compare the left hand side, what we have is TdS is 1 by beta d g plus beta E bar plus gamma n bar, which is essentially I can write my ds as one by beta t d of g plus beta E bar plus gamma n bar, and beta is 1 by kBt. So, this will give me kb d of g plus, I can also write beta as 1 by kBt here, and I can write my gamma as minus mu by beta. So, I can write my gamma as minus beta mu, so mu by kBt n bar. So, if I compare this, what we have is S is equal to kb and G was my ln Z plus E bar by T minus mu n bar by T. If I now compare with the absolute value of internal energy that we have found earlier, we have found that E bar or E is equal to Ts minus PV plus mu n. So, when I write these expressions, I do not put a bar there typically. So, if I put that thing right here, what we have from here is Kb ln Z plus E minus mu n by T, that is Kb ln Z plus Ts minus Pv by T. So, you have cancellation of the entropy, and what we get is minus Pv is Kb T ln of Z. If I compare with the earlier case, what we had was F is equal to minus Kbt ln Q for the canonical, with what I am getting in the grand canonical ensemble. You may say that just like my Helmholtz energy was the thermodynamic function that we had to minimize for the canonical ensemble, PV becomes the thermodynamic function in the case of a grand canonical ensemble. So, that is simply equal to minus Kbt ln Z. So, we can also get it by using Legendre transformation. Let us see how it works. So, basically we have to go from the Helmholtz free energy, that is a function of TVn, to some potential omega, let us call it omega, as a function of T V mu. So, essentially n has to be replaced with mu here, and that thing is coming from the Legendre transformation. So, first of all, we know that F is equal to u minus Ts, but in this case omega is F minus mu n, and so this will be u minus Ts minus mu n. We have been using the notation E for the u in our case, and E is equal to Ts minus Ts plus mu n minus Pv. So, this pretty much gives me minus Pv in this particular case, right. So, therefore, what we have been able to establish is that for the grand canonical ensemble, the thermodynamic function that we can also get by Legendre transformation gives me a value that is equal to minus Kbt ln of Z. So, the thermodynamic function essentially relates to the partition function in pretty much the same way in every ensemble. In the canonical ensemble, the thermodynamic function was F. In the grand canonical ensemble, the thermodynamic function is omega, that is equal to minus Pv, which is still minus Kbt ln of the partition function, just like what we had for the canonical ensemble. F is equal to minus Kbt ln Q. The definition of partition function has changed, but the relation between the thermodynamic functions and the partition function has not changed. The relation between the average of properties with the partition function has not changed, and therefore, once we do this kind of a toolkit for a particular ensemble, the same toolkit can be more or less employed for every different ensemble, just keeping in mind that the partition function in there have changed. In fact, the partition function Z relates to the canonical partition function. We can see how it happens. So, Z is summation of n, summation of j, exponential of minus beta e n j minus gamma n. This I can as well write as summation of n, summation of j, exponential of minus beta e n j multiplied with exponential of minus gamma n, and this quantity actually is my canonical partition function q. So, therefore, my grand canonical partition function is simply a summation of n of the corresponding canonical partition function when n was held constant multiplied with exponential of minus gamma n, and gamma we have already discussed relates to the chemical potential. In fact, this can be related to something that is known as the activity of the system. So, we can represent this as something like lambda to the power n, where lambda is exponential of minus gamma or exponential of minus beta mu. This is what is referred as the activity of the system, right. So, we can also go back to thermodynamics and find the different ways in which chemical potential is represented, and all of this essentially come from the definition of the partition function. So, to conclude the discussion, what we have done in this particular case is that we have derived the partition function of grand canonical ensemble. We showed that the properties we could evaluate for the canonical ensemble, we can still evaluate in the grand canonical ensemble using more or less the same definition. In addition to that, you also have the average number of molecule that is meaningful in the case of grand canonical ensemble, that also we can get from the partition function. And finally, grand canonical partition function is related to the canonical partition function. In the last bit, what we can also show that the fluctuation in the number of molecules is also related to the partition function in pretty much the same way the fluctuation in energy was related to the partition function in there. All that will change is that now I am looking at n in place of E. So, you will have sigma n square, that is the variance, is n square minus n bar square, and we can pretty much do the same math as we did for the sigma E square in the canonical ensemble and find that my sigma n square is given as simply dou n bar by dou gamma with a minus sign. In fact, sigma E square is also related to the average energy with pretty much the same formula that we had for the canonical ensemble. So, in a similar way, we can find the fluctuation of quantities also using the partition function. And why I am saying that? Because this n bar and E bar can be evaluated again as the derivative of the partition function. So, essentially the fluctuations or the variance is characterized by the second derivative of the partition function in the grand canonical ensemble, and the same was true for the canonical ensemble. In the next class, what we will do is we discuss what is known as an isothermal isobaric ensemble, in which case the control variables are the number of molecules, pressure and temperature. And in that case, until so far what we have done is the volume was constant, but in that case the pressure will be constant, or the pressure will be the control variable in that particular case. And as you know, we expect to get the Gibbs free energy as the thermodynamic function, and we will have a partition function for that particular ensemble that will be clearly different from the partition function for ensembles we have done so far, but it will still be a generating function, and the way we are evaluating the average properties are still going to be the same in the isothermal isobaric ensemble. So, with that I conclude here. Thank you.